Folks, in this video we want to derive something called the law of sines, and in the second video we'll utilize it to help us solve a non-right triangle. So it's worth mentioning this, folks. In this course we've largely focused on right triangles. That is, triangles where one of the interior angles had a measure of either 90 degrees or pi radians. That's what we focused on. We now want to turn our attention to solving specifically non-right triangles. So to do that, we're going to use either the law of sines, as we will in this section, or later the law of cosines. In this section we'll focus on that law of sines. So again, if we have a 90 degree or a right triangle, a triangle with a measure of 90 degrees or pi radians, we have all sorts of extra tools, for instance, and most importantly, the Pythagorean theorem. But for non-right triangles, we don't have that. And so the law of sines or the law of cosines will help us. Let's jump into this problem here. And let's remind ourselves of the area of any triangle. Well, the area of any triangle can be written as 1/2 the base times the height. So just be careful here, folks, because these letters show up all sorts of places. This is base. I don't think there's any room for confusing that, but this is height. So that is not necessarily a hypotenuse of a right triangle, and non-right triangles do not have hypotenuses. Okay, so what I'd like to do here is I'd like to find the area of each of these three identical triangles. And these three triangles, they are identical. You can check at the best of my ability to draw them. And let's go ahead and find their areas. Okay. So for the first triangle, let's go ahead and number this. I'm going to number this as triangle number 1 here. And let's go ahead and find its area. To do so, what I'm going to do is I'm going to compute its height somehow. So one way we can compute its height is to go ahead and create a larger right triangle that this is a part of. And so let's call this right here the height of this triangle. Okay, so in this case, the area of triangle 1, well, we just said that it's 1/2 the base times the height. Here, somewhat fortunately, the base is labeled as b. That won't be the case for all of these triangles. But then we've got to determine how are we going to find this height. Well, the height of this triangle can be obtained by using this angle C right here and using my hypotenuse side. Okay, so again, the original triangle is not a right triangle. It does not have a hypotenuse. But if I construct this other triangle that I did here, then I can imagine this larger triangle as having a hypotenuse of side length A. And so we know the sine of angle C would equal the ratio of the opposite side of angle C. So for C here, this is its opposite side, all over the hypotenuse side of the larger right triangle, which is A. And if I do some adjustment here, if I solve for h, we would get that h here is equal to a times the sine of c. So we'll replace this h right here with a times the sine of c. Okay. Let's just put that on the back burner. Okay, for this second triangle, for triangle number 2 here, we're going to do something similar. We need to somehow obtain the height of this, and as I've set it up, we're imagining the base of this triangle as side length a. So let's see what we can do here. Well, we get always that the area of this triangle is 1/2 the base, which we're labeled as little a there, times the height. And here, this is getting a little messy. I'm going to use a different color here. I probably should have done that for the first one. Let me do that here, just to make that a little easier on the eyes. And here we could go ahead and construct one of two different right triangles. I'll go ahead and pick this one right here. And so, while we're not trying to find the area of this smaller right triangle, we do want to find the height of this smaller right triangle, which I've labeled as h. And let's go ahead and use angle B to help us out here. And so if we go ahead and use angle B to help us out here, we would have, let's see here, let's make a statement here that the sine of angle B is equal to the ratio of, so for angle B, I'm talking about this smaller right triangle right here, which is the ratio of its opposite side, which is the height, all over its hypotenuse, which is c. So again, the original triangle, folks, does not have a hypotenuse. But the smaller, in this case, smaller right triangle that I constructed does have a hypotenuse, and we've labeled that as c. So then we would find that c times the sine of b is equal to h, and so I'm going to take this, so normally this would be h here, for the area of a triangle is 1/2 the base times height, and we're going to go ahead and substitute in for the value of h, c sine of b. Okay. So again, let's put that on the back burner, and let's go to this third triangle here. So I think we should be getting a sense of how this works. I'm going to move my picture down just a little bit. That was a little bit of a poor decision there. I'm going to scoot that down just a little bit. Make that just a little smaller. Let's clean everything up just a little bit. Oh, can't do that. Just to give us a little more room. Okay. So for this third triangle here, I'm again going to try to set up to find its area, and its area will be 1/2 its base times its height, and in this case we'll use as the base of this triangle, we'll use c here as the base. And we need to come up with the height of this triangle, and so if I were to construct this right here, we could use that right triangle to help us find the height. And folks, I've sort of painted myself into a corner. I was wanting to do this proof for a for a triangle with an obtuse angle. So this will be slightly harder than I intended for it to be, but I think we can still do it. What I'd like to do here for where I'm going, and there's other ways you could come up with that height for sure, but for where I'm going to go ahead and reference this angle right here to help me come up with the height. Okay. And so what do we know about this angle? Well, we know that it would be supplementary with the given angle A. That is, the sum of those two angles, A and this other angle, have to add up to 180 degrees, or pi radians. And so I'm going to go off to the side here because this will take a little bit of computation, but we want to come up with h. And so we know that in general, if we were to take the sine of, here I'm going to write this as 180 degrees minus a, is equal to the ratio of this height right here, h, over this hypotenuse, b. So I am looking at this smaller right triangle, as opposed to maybe you were thinking I would use this larger one, but the problem is that would give me a expression in terms of b, and I already have that. That's why this has gotten just a little bit harder than I intended. So we know that h is equal to b times the sine of 180 degrees minus a. And I just want to clarify, does that make sense that is 180 degrees minus a? Well, we know that if we added a to this angle, we would get 180 degrees. And so that missing component, the supplementary angle to a, is 180 degrees less a. So now what I'm going to do is I'm going to go ahead and use my sum of two angles identities, in this case it'll be a difference because of that minus sign, to find out this expression here. So remember, when we take the sine of a difference of two angles, that would be the sine of 180 degrees times the cosine of a minus the sine of it, let's write it this way, minus the cosine of 180 degrees times the sine of a. And when we clean that up, fortunately, the sine of 180 degrees is 0, so that whole term vanishes. So since the sine of 180 degrees is 0, we don't have that term in our difference of sines, so I'm just left with b times minus the cosine of 180 degrees times the sine of a. And again, folks, this is just a little bit harder than I intended. I'm just trying to come up with this expression for h right here, but I think we can still use some of our earlier tools to get through it. So what's the cosine of 180 degrees? Well, that's -1 times the sine of A. And so what we end up with is that our height is just equal to b times the sine of A, and that sort of fits the pattern that we've had in all of these cases. It was just a little bit harder because this angle A right here was obtuse. Okay, so back to computing the area. We're trying to find the area of this triangle right here, and we said it was 1/2 the base times the height, and we're using C here as our base, and then we just had to do a whole bunch of work to find the height. If I lost you on that work, folks, that's okay. I think that keeping track of those other two examples might be more helpful. And if you have any questions about this, please come by and see me, and I'd love to chat with you. It's not essential that you've followed all that to know where we're going. If you just want to accept that this height right here is equal to b times the sine of A. And so what we end up with is that this is equal to 1/2 C times the height, which we're going to replace with b times the sine of A. Okay, so we're moving right along, and now we're ready to finish deriving the law of sines. How come? Because all of these areas are the same. So we know that 1/2 BA sine of C is equal to 1/2 AC times the sine of B, which is equal to 1/2 CB times the sine of A. So now what I'll do is I'm going to group together pairs of these equations. All three of these are equal. Let's group together pairs. So let's just group together the first two. So if I just group together the first two, we'd have 1/2 BA sine of C is equal to 1/2 AC times the sine of B. In this case, the two factors of A will divide out, as will the two 1/2s. And so we're just left with the statement B times the sine of C is equal to C times the sine of B. And what I'd like to do is I'd like to first divide both sides by B. So I've divided both sides by B, and now I'd like to divide both sides by C, which gives me the sine of C over C is equal to the sine of B over B. Okay. Now what I'd like to do is go ahead and grab the second two equations and set them equal to one another. So we know 1/2 AC is equal to the sine of B, which is equal to 1/2 CB times the sine of A. And in this case, the 1/2 still divide out, but in this case the factors of C divide out. And here we're left with A times the sine of B is equal to B times the sine of A. And if I divide both sides first by A, that would give me the sine of B is equal to B sine of A over A. And now if I divide both sides by B, we'd get the sine of B over B is equal to the sine of A over A. Now what we can do is we can put all three of these ratios together. So this is equal to this expression, and that expression is equal to this one. So putting these all together, we get what's called our law of sines, that the sine of A divided by little a, side length A, is equal to the sine of B divided by little b, which is equal to the sine of C divided by little c. Folks, this was a tough derivation. If I lost you on this, I would encourage you to wait a couple days and then try this video again to see if it makes a little more sense the second time through. But it's not essential that you be able to derive the law of sines. Instead, I'm asking you to make sure that you have the law of sines memorized in one of its versions, and this is the version I've presented here. So folks, if you found this challenging, this is our take-home point. We call this expression right here the law of sines. And the big takeaway is that we use the law of sines when we're working with non-right triangles. All right, I'll see you in the next video where we put this into practice. It'll be a little bit more concrete.